These are the parts for the crankshaft, and this crankshaft is from a lift-on motor. I believe it's 125 cc, and I disassembled the parts so that I can measure and 3D scan the parts. So basically, based on the 3D scans, I can build a true model. This one is the magneto side crank cheek, and so this is the crank cheek. Basically, this is the counterweight side, and then this is the shaft and spindle that drives the magneto. This one is the drive side. Again, this is the counterweight part. This is the section that holds the crank pin, and then this is the drive side, and you can see the spline on it and a threaded section. When I disassembled this, I found a lot of interesting things that I want to describe here. So one of the most important things, the way the oil will get to the connecting rod. So there's a cover on this side right here, and there's an adjustment screw, and there's a pump up here. The pump is pushing oil around the housing in a cover, and from the cover into the end right here. So the actual oil path is being diverted two ways. One goes up to the cylinder head and one goes right here, and there's a nominal gap, so it's really important to have this adjustment screw properly adjusted. Otherwise, this gap right here is going to be too large, and there's a chance to deprive the connecting rod bearing from oil. So once the oil enters here, there's a little hole right there, and through this hole they're gonna lubricate this bearing here. So there's a clutch in this motor, and you know, the clutch can be stationary, it can be rotating relative to the crankshaft, and this hole is lubricating that bearing. The most important thing here is basically this hole that goes all the way to the end, and then there's another hole here. Okay, trying to show it so you can see it. You can see the screwdriver goes into that hole. So the oil from the center section comes through this hole, just like you see, and then once this pin is installed, it will enter into the pin through this gallery, and then there's a cross-drilled hole, and through this cross-drilled hole on two sides it's going to lubricate this main connecting rod bearing. This hole on the other side is just a blind hole. I believe they use it for the assembly, for alignment, because it's really important to align this hole properly with that hole. So when we put it together, they should be aligned. Otherwise, you know, if it's 30 degrees off or even 5 degrees off, the oil is not going to get where it's supposed to go. So I disassembled this crankshaft, and I did the scanning. The white powder residue is actually from the scanning process. We use a some kind of shoe cream or shoe spray. I believe it has some kind of stuff in it, and talcum powder. Normally just put talcum powder in a shoe if it has odor and takes care of it. Well, this one is in a can, dispensable, and you can spray it. It's perfect for 3D scanning. 3D scanners don't like shiny objects, so they have hard time capturing shiny surfaces. So once we spray these shiny surfaces with that powder, that spray, it will help a lot with the scanner. Basically, it's to replace the 3D scanning powder you can buy for 30 bucks. This shoe sprays is in a range of $1.50 or a couple dollars maybe. So I used a hydraulic press to press out this pin and disassemble the parts. And then the next thing was, once I was done with the scanning, to assemble it back on. And that wasn't a successful process. I mean, just look at this guy, how he does it. I'm nowhere near close, and I want to have a crankshaft that runs true. It's not absolutely true. It's never going to be absolutely true. You're going to always have some kind of error. The idea is that when the pin is installed and these two shafts are rolling on some kind of support, then you're not supposed to have a wobbly motion like such. This is exaggerated, but you get the idea. So I basically tried to assemble it and I failed. I didn't have the proper support, and you can see some of the imprint here from the pressing when I was pressing in or out. I don't remember. It was actually damaging the parts. So what I have done is I come up with my way of assembling it. So based on the 3D model, I was able to design a frame like this. So you can see this frame uses 1/4-inch pins, which will align the parts properly. And furthermore, I marked the corners. So basically, when I cut the parts, I put the assembly together, bolted it, and most importantly, on the same setup, I drilled this hole and this hole. So these holes are to accept the crankshaft halves. So this is the drive side, so it goes in like so. Okay, and then here I can put this spacer, and then this is the nut from the actual engine. So this nut is gonna hold the clutch. I have an old bicycle wrench here, so I can put it together like so. Okay, so it's just to begin with, and I'm not tightening anything yet. So now I can align these holes. There's a little clearance on both sides. This is just to be able to insert the pin. And now I can take the other side and then assemble. This is the magneto side, and then put this tack of washers and spacers on just like that. Assemble this nut, and then you can see I have a hole here, which should be concentric with the pinhole. So I'm just going to eyeball it a little bit and then tighten this up. So once I have these two, then I can put them together like so. Okay, need a hammer. Hammer time. Okay, so here's the proper tool for the job. So I'm just gonna tap it together like so. Looks like we got solid stack. Now I can install the bolts and bolt it together. So once the bolts are installed, I can tighten them, and then I can align the crankshaft halves. And once those are aligned, then here is my plan. So tighten these up like so. So you can see it's nice and solid stack here, solid stack there, same here on this side. So what I can do is I can insert a pin, and I've measured the bores in these holes that would hold the crank pin, and I came up with a tool like such, and I've actually done a couple of them. So this is 2495, 2496, and then this is for 24943 and 954. I just prefer this one because it's got a threaded handle, so if stuff gets hot, then it's not gonna burn me. So I can insert this hole, this plug like so in a hole, and make sure that these two halves are aligned. And so the plan is to take the pin and put it in or put it on dry ice. The dry ice is minus 74 degrees Celsius, and this is a 25 millimeter diameter pin. So if I put it on dry ice and I cool it from room temperature, then it's gonna shrink about 27 microns. And the other part of the equation is to put this whole assembly without the pin, to put it in an oven and heat it up. And so I was wondering, you know, how hot it should get, and I did some back of the napkin calculation, and it came out around 250 degrees Celsius. Well, first I tried a toaster oven. That didn't fly because it only went up to 150 degrees. So then I pulled out my old kiln from the storage and fired it up, and basically that did the trick. So I measured the ramp up rate of the kiln, which doesn't have a temperature control right now. I am the temperature control, so I should stand there, basically plug it in, plug it out, and heat soak this part, this assembly, for about an hour. Based on the mass, that's why I calculated it will reach the 250 degrees. So then I'm gonna have enough clearance to take the original pin and just basically drop it in with the connecting rod installed, so I can put this whole assembly into the oven like so. And you can see there's a little notch here to hold it properly, and I can just go and align the parts, you know, tighten up the nuts and screws and bolts and everything, and just basically pull this out and then drop in the pin. Now it is really important how the pin is assembled. Again, this is the drive side and this is the oil gallery, and so I made a little arrow here showing you the arrow, okay, and then these two lines. So I should drop it in this way, and hopefully it will go in. I give it about 5% chance that it will work. There's actually a higher chance that it will not work because of things I didn't consider. But again, this kind of science, and I want to see if I can pull this off. So that's the plan. Let's see how it works. Suspense is building. This is the kiln, and again, this doesn't have a controller. So if I open it, you can see the parts inside. It's getting toasty. I got a data acquisition here. So this guy is measuring the temperature in the kiln. We are running 132 degrees Celsius, and then in the cooler -61 for the pin. So if I move this up here and peek inside, you can see the pin, and I install the thermocouple inside the pin, so it's cooling the pin down. I'm gonna close this. I have no idea about the half-life of the dry ice. I'm guessing it will be gone by tomorrow. This is a fairly expensive experiment, I'm telling you. Started all this about 2 years ago, and finally I'm at the point right now where I put everything together. Obviously I have tons of other projects in the meantime, but that dry ice, it was $7.60 for a pound. There's 2.5 pounds, so it was around $18, and I think I'll have to run it for about an hour and basically watch the kiln and make sure that it doesn't really exceed 250 C. And I was already doing the measurement today on the pin, and it will go down to -74 C, and I only measured about 16 microns of shrinkage on the pin, so that worries me, but we'll see when everything goes together. So I put an extra thermocouple on the part, and it is showing 258 right now. The kiln is at 310, and pin is at 72.6. Here's a magnet. It's a strong rare earth magnet. I'm going to try to use this to put the pin in here. So here comes nothing. Ow. This thing is hot, and it's really, really hot. So I'm gonna use this to set it up like so, and there's the pin, and the pin slides out easily. Now all I need to worry about is mist. So we're gonna put it in there, close this, try not to touch that, and open this and grab the pin. And thanks God the pin is still magnetic. Ow. Well, that wasn't smart, putting my hands in there like so. So here comes nothing. Again, I give it 1% chance, and it didn't work. Ah, this magnetic trick. It. Oh, that's it. Test 1, complete and utter failure. I need to wait until it cools down. Well, today's tomorrow and it's raining outside. You can hear the rain and the thunder. Makes it even better to work in the workshop. It turned out that the half-life of the dry ice is about 1 hour in the cooler that I stored in. So basically the dry ice was gone. By the next day I didn't have a chance to do a second test. So what I mocked up here is basically 1/2 of the crankshaft, and the idea is to press in the pin about halfway, orient it properly, and this washer just happens to be the right size to lay underneath, and we'll see how it goes from there. I need to make sure everything is aligned properly. This pin is aligned properly. So hopefully that will do it. We're gonna start pressing. Now, this is gonna take forever if I don't close the valve. Looks like she's going in. So there you have it. The pin is basically halfway in, and now I'm gonna use the jig, put together the jig to align this pin with the other half. So now I can assemble it together, put on the bearing and the connecting rod. Like so. Oh, look at that. When it's in focus, it's even better. It looks like these two are flush right now. So the problem now is this is going to sit in a press like so, so it's going to be vertical. And a lot of that force is going to be right here in this section. But there are these washers underneath. So I gotta reconfigure this to have as much surface area underneath here as I can, so that this can sit in a hole in a press plate, but I have a lot of surface area, so it's not gonna buckle this plate here. You guys ready for this? This is the final press in, and I aligned the parts, removed those bolts and nuts that previously constrained them together. Now I can feel that there's some serious press force going on, and you can hear that press is suffering. There's definitely a lot more force pressing in the pin. Now the problem is, I don't know how far should I press. Looks like it got down all the way to the bottom. Based on the force I can feel on the handle. Yeah, looks like it went completely in. So we got the pin completely seated, and you can see she's free to rotate. Now the problem now is that it locked in the connecting rod. So I'll have to come up with something to press it apart a little bit. But as far as it goes, it's free to rotate. There wasn't much clearance here in these journals when I bored it, and you can see it's not really wiggling there. So there's a good chance that this shaft and this shafts are coaxial. Looks like operation free the connecting rod worked. All I did is supported it right here and then applied pressure to the pin just a little bit, and that was enough to get rid of that press between the two halves. So now the connecting rod is free to rotate. It's ready to go. Thanks again for stopping by and following me on this journey. Again, if you like the video, please give me a thumbs up and subscribe. Thank you. Bye.